Let's begin our today's class. I think we made it into PKI last week, and then we ran out of time. So the story is that we are talking about now public key cryptography, and then we start to plan out what is the advantage of having public key cryptography. So in the case of symmetric key, if you wanted to contact, communicate with n person, so you have to, if you have a group of n people, you have to share a different key with any other party. So later on we are in the beginning of the www, and so these are not the people, this could be the servers that you want to communicate with, and having this assumption that you have met these servers, you have walked into these offices and pre-share a key would be something that would not be feasible for the concept of the internet. And that was the case where people start to think that we should have a different approach. And there, the public key cryptography were born, where right now everybody would have a sort of a public key and a private key. Think about it as a public key as your email address, and private key as your secret key to that email address, and then you could go to your inbox and check your messages. So we would have the same concept. We would store everybody's public key into some online repository, just show it as a DB, and then whenever you want to send a message to somebody, for example, over here, this user 1 wants to send a message to user 2, you just ask that, what is the public key for user 2? And then you can retrieve those information, and then you can use that to send your message secretly to only user 2. So that is the concept. And then I think throughout this lecture over here, we would spend some time to go through different options that we have for how to build one. I know that RSA is an option, so there are a lot more to learn about RSA. So today, hopefully, we would be able to close the loop on RSA, learn it, and then discuss about the weaknesses, and then how we can patch it, and all many different stories that hopefully we would cover it today. But before we get into there, just like usual, let's clear out some notation. So if you're talking about public key encryption, so we would have encryption and decryption algorithm. So the decryption algorithm would take two parameters, the public key and then the message. And sometimes we just show it like this. So encryption of public key of message M. So given this public key, then it would output the C ciphertext. And on the decryption part, the decryption algorithm would take the secret key along with the ciphertext, and then we also sometimes denote it with this notation, and then it is supposed to retrieve the message. Along the lecture today, we would also start to discuss about digital signatures. So the digital signature, we have two different algorithms that sometimes, for some crypto systems, not necessarily all of them, they would look very much the same as encryption and decryption, for example, for the case of RSA. But you can think about it that it works in a reverse way. So remember that for encryption, we always use a public key and a message to encrypt. But right now, when you want to sign, you can't expect people to use your public key to verify. You use your secret key and the message so that you can generate a signature. And sometimes we denote it like this: secret key with the signing algorithm with secret key, and it would output the sigma, the signature of this message. And then once that's given, we have the verification algorithm, that the verification algorithm would take the public key, message itself, and then the signature. And sometimes we also denote it like this, and then it would only output a true or false. True means the signature passes, and then false means that the verification has failed. So let me give you an example over here. It could be confusing sometimes. So remember, we have our players, Alice and Bob, and let's say Bob wants to sign a message and send that message. Alice wants to sign a message and send that message to Bob. So we know that Bob can have access to Alice's public key, right? So he knows the public key of Alice, right? He can go to that DB online repository and ask what is the public key of the Alice. So now that Alice wants to sign a message, it wouldn't be useful for her to also use her own, public key. So you can use the public key to sign and public key to verify, because if she uses the public key, well, everybody has that public key, right? So everybody can sign a message. The only thing that nobody would have it except Alice is the secret key corresponding to this public key. So Alice is sitting here with the secret key of Alice. And then what she would do is that when she's sending a message to Bob, she would also sign this message. So we would say sigma equal to the signature of using this secret key of Alice, and then the message itself, right? So she would be able to compute the signature and send it to Bob. The good advantage of using the signature is that, well, we suppose that Alice wouldn't share her secret key, so she would be the only one who would have access to the secret key. And if Bob received a message, and what he would do, he would run the verification algorithm, so verification using the public key of Alice, and then he would pass the message and the sigma itself, and then he would have two outcomes, whether it would be true or it is false. In case of true, he would say that, okay, this is the message that was indeed signed by Alice because I use Alice's public key and it verifies, right? So this way, Bob is convinced that this message also can convince that it's coming only from Alice, because she's the only one who got this piece of information, secret key, and nobody should be able, unless the signature scheme that they're using is breakable. So we assume that the underlying signature scheme that they use is secure. Then there should be no way for anyone else to, without having Alice's secret key, to generate a valid message, a valid signature for any message. That's what we call it, existential forgery. So this is the concept, and we have pretty strong, signature schemes out there. RSA is one of them. Gamma signature scheme is another one, and then the one that you're using most of the time on the web is the DSA, digital signature algorithm. That is the standardized one that most of the communication on the internet would use the DSA algorithm. The good thing is that we would be able to cover most of them on this lecture. So you would learn multiple different signature schemes at the same time, and then you could see that which one has a higher advantage on different scenarios for you to use. All right. So this leads us to the RSA encryption algorithm itself. I think we've discussed it sometime before, but today is the time that we would go a little bit more deeper into this algorithm and see how actually this algorithm works. So typically for an public key crypto system, we are looking into three algorithms. So we have key generation, we have encryption, and then we have decryption algorithm. So these are the three basic things that we want to have them in place. We talk about public key, private key. So we should have an algorithm so that it can help us to generate those keys, right? We can't just assume that the public key and a secret key exist. So we have to generate them. So let's see, how do we do that for the case of RSA? Everything starts with choosing two big prime numbers, right? Remember that we had some algorithm discuss how we can find it. And it's very possible to find two prime numbers. So we would quickly find two prime numbers, pretty much large ones, and then we would multiply them together to compute n, which is equal to p times q. So now that we have So we are trying to form a group called Z star N, right? And then we know that the size of the Z star N, we know that Euler told us that according to its function, Euler function, we know that this is going to be equal to N, which is equal to P minus 1 times Q minus 1, right? So this is what we have from the Euler theorem. All right, so since we have the P and we have the Q, we have no problem computing N, and then we have no problem computing phi N. And then now we can form this group, right? Z star N. All the elements that are integers that are smaller than N that are co-prime to N. All right, so that is set. So the next step, this is like a step 1.1. And a step 1.2, what we have to compute is, oh, I'm sorry, this is maybe 1.2. And this one to be 1.3. So we're gonna choose an integer E. So where E is less than N. And then so that E is co-prime to phi N. So we remember that we have this phi N. Normally what we would do is like you choose some prime E, right? You're always safe that it couldn't be a factor of phi N for most of the time. And then we compute D to be the inverse of E mod phi N, right? So we know that by extended Euclidean algorithm, if E and phi N are co-prime, we can find we can solve this equation. E times D equals is going to be 1 mod phi N, right? So we know that we can have this equation. Or sometimes over here that I just want to show you where the other equation comes from, we can also represent this one as ED equals to K times, some K times phi N plus 1, right? There is some K that you divide, when you divide E to phi N, there would be some K times and then phi N plus 1. So this is the different way to present this equation. Okay, just keep in mind. So that now that we know how to find the inverse, we use the extended Euclidean algorithm, and we can quickly find this D that happened to be the inverse of E, because E times D equals to 1 mod phi N. And then now we're done. So the only thing that we have to do on the last step, 1.4, is to set the public key to be this integer E and N, and then the secret key would be the inverse of E, which is D and N, and that's it. Only 2 integers for public key and only 2 integers for secret key. So what this user can do now is that this user is going to publish his public key. We would share it to everybody, just like, as we said, an email address concept. And then this user is going to keep the secret key secret and do not share it with anyone and just keep it for him or herself. So now that is given, that this user has published his or her public key to everybody else, then some user can start to encrypt the message and send it to this user. For example, we can encrypt, given this public key of our user, we can encrypt this message M by computing M to the power E mod N, which would be your ciphertext. And we would be able to send this message to this user. And then once this user receives a ciphertext, he would use his secret key, which is, we have D and N. So he would compute C to the power D mod N, and he would retrieve the M. Looking into this computation, these are fairly easy computation. Remember that we have a modular exponentiation algorithm that we show that, the order of this algorithm is the log n of n is the number of the bits in E. So, we can achieve and do this computation quite fast in some sort of logarithmic scale. So in that fashion, we are fine. And then the only restriction over here is that M should be some element from Zn, which means that M should be smaller than N. So if user if this user expects to receive some long messages or long integers, then it means that he should choose longer P and Q so that N becomes quite large that can cover than M, right? That is one incentive. And then the other incentive is that according to the factorization problem that we've discussed many times, if you choose a larger integer, you know that factorization of as the integer gets larger, it becomes more difficult. So that security is another reason that somebody would want to choose a higher P and Q. Let me put, this is what your textbook would tell you when you study RSA, but well, I'm not satisfied with how your textbook would explain this. So allow me to explain it in my own language. All right. So let's have a better discussion of how this algorithm should work. So if I was the designer of the RSA, there were two pieces of information that could have used to help me to design this algorithm. So let me write them down so that we can discuss that. So first of all, from Euler, we know that, from Euler, the property number one, I would just want to call this one, we have two important properties that are building blocks of RSA. We know that if I get any message, I raise it to the power phi n mod n. This is going to be, I'm sorry, let me write it this way. It's going to be 1 mod phi n. Oh, sorry, mod n. How so? Let me give you an example. Remember when we were talking about the Z star P, the group that are integers that are coprime to P and are smaller than P, all the integers from 1 to P, basically. And we said that if you choose any element A, if you get any integer A, you raise it to the power P minus 1, you will get 1 mod P. Why is it so? We said that the order of this group of ZP is P minus 1. And then we had this discussion together in the last chapter that if you take any element from a group and you raise it to the order of the group is the number of the elements in that group, then you will end up to the identity element, which is 1. This is the Euler's theorem. So for the case of Z star n that we are discussing over here, for the case of Z star n, we know that the order of this group is phi n. Phi n is going to be the order of this group, Z star n, right? Okay. So that's what we know. So basically, it is now it is clear that if we get any message, any m that is less than n, and then we raise it to the power phi n, then the result would be 1. This is given by the theorem. Okay, so this is what we know. And then we also have another fact from extended Euclidean algorithm. This is going to be your fact number 2. We know that if we choose a e and we choose some integer like e that is coprime to phi n, right? Then it means that the GCD of this e and phi n is going to be 1. And that means that we can find the inverse of this integer. So using the extended Euclidean algorithm, we know that we can find a d such that e times d equals to 1 mod phi n. Or again, we can show that it is equal to ed equals to some k times phi n plus 1, just different representation. So we have these two pieces of information. Given the group Zn, if we get any element from this group, we raise it to the power of the order of this group, the size of this group, then we get 1. And 2, if we choose any element E that is over here, that is co-prime to phi n, then we can find the inverse of this E, okay? So this is given. So let's see why does it help us to, how did these 2 pieces of information lead it to find or compute the RSA. So I want to have this, show you this formula that for any M, so M equals to M to the power ED mod N. So this is all RSA is about. Let's see what does this mean. So according to this formula over here, we can replace ED with K phi N plus 1. So which means that I can say M to the power K times phi N plus 1 mod N. And then I can break down this one and I can say that it is M times M to the power K phi N times M to the power 1 mod N, right? So now you see that I'm raising this M to the power of the order of the group. So according to the rule number 1, this should be 1. So according to the rule number 1, I'm going to have, I'm going to use that property. So let me show it clearly. M to the power phi N, and then I raise the whole thing to the power K times M mod N, right? Now this is clear, right? This whole thing would become 1. So 1 to the power K is just 1. So this is going to be 1 times M, right? Which is going to be M, right? Mod M, right? And this is going to be M. So we have this equality, and that is correct. That is magic, right? So as long as we find the inverse of E, and then we multiply E to this inverse, and then we expand this formula, and we show that, oh, actually, if we take M and we raise it to this power, E times D, then the result is going to be M itself. So how does that help for the case of cryptography, for the RSA? So let me show you like with the clock arithmetic. So we take our M here. Let's say we have our M. And this is my C. Okay, so the first part is that I compute, I can break down this computation in the half. That's the idea. So I take M, I raise it to the power E. So it will compute M to the power E mod N, and I get to C, right? And I get C, and I, some intermediate results, and I raise C to the power D, and that would I compute C to the D mod N, right? And that would return me back to here, which is equals to M to the power ED mod N, right? So essentially what RSA people have found was that, well, it looked like that if we raise any M from N to this power ED, and we know that what is the relationship between ED, it just cancels the effect and we just get back M. So why don't we just, break this computation? If we do 1/2, we get the M to the power of E. We get to some intermediate result, which we call it C. And then when we get C to the power D, we would get back to M to the power ED, right? So if you look at here closely, C is basically, let me write this down over here a bit more nicely. Oops. So we say that C to the power D mod N, right? C itself so far is M to the power E. We raise this one to the power D mod N. Remember, this is going to be equal to M to the power ED mod N, right? So this is the whole story that is happening over here. what we are doing is just we are breaking down the computation, and then we would just halt in the middle, which is the intermediate result, and then we use that one as the ciphertext. So I think now if we go back to this page, I hope now that you have a better understanding that why we would raise m to the power e, and then later we raise a ciphertext, which is our intermediate result, to the power d, and of course we are able to retrieve the message. So I hope that this different representation that I always try to show with like clock arithmetic, you take some m, you do some computation, we are in a circle, in a clock arithmetic. So we can basically, based on different E and D that you choose, then you will map this M to different locations for C, right? That is now very clear. But no matter if you have to choose different E's, then you find the corresponding D according to this Euclidean that is inverse of this E, using the extended Euclidean algorithm. Then no matter what different value for E or D you choose, as long as it satisfies this property, then this encryption system would always work. And it is just the magic comes from two facts that was just there, right? Euler proved this for many years ago. Taking any element, raising to the power of the order of the group, you get 1. And then the extended Euclidean algorithm was also there for you to compute the inverse of an element. But it was just a smart way that the RSA authors, which every letter correspond to initial of their last names, they sit together and they notice that they can use these two properties to design a very strong, crypto system. So I hope that this is now much more clear, at least in details, and based on the small background that we talk on, background on number theory that we explored together on the previous chapter. Now you have a deep understanding that why RSA works, right? So let me pause here to see if we have any questions. Okay, so let me go back to this previous page. There was one more condition that I didn't talk about it yet. And let me change even my pen color. Okay. Homomorphic property. That's such a big name. But it's if you are familiar with cryptography, there is always a very hot topic that people are talking about, homomorphic encryption system, or more advanced one, which is fully homomorphic crypto system. And these are some properties, some nice properties that not every crypto system would have, but naturally with the design of this RSA crypto system, we have this property. So let's see what are we talking about. So essentially, what homomorphic property here is saying that if you use somebody's public key, and then you encrypt the message M1, integer M1, and also under the same public key, you also happen that you encrypt some other integer M2, and then we know that after encryption, this is going to be C1, and then what it's saying is that if you multiply C1 times C2, okay, you get a new ciphertext C3 that this one is equivalent of encryption under the same public key of M1 multiplied to M2. So it looks like that when you multiply these integers, you are basically multiplying the the original messages as well. Let's see through mathematics why does it look like that, and then we go through some example and see what is the advantage. So what is the encryption of, let's expand this equations over here. So the encryption of M1, I can say that it is M1 times E mod N, and then we are multiplying to M2 to the power E mod N, right? And then I can show that this is equals to M1 to the E multiply to M2 to the E mod N, which is equal to M1 times M2 to the power E mod N, right? Very interesting, right? We just multiply the ciphertexts, and then it is the equivalent of multiplying the plain texts itself. So, for example, if I do encryption with the public key of, let's say, 5, and if I encrypt under this public key integer 5, and I multiply to another encryption of some other integer, let's say 11, and if I multiply these ciphertexts together, what I would have is the encryption, still encryption, under the public key, the same public key of 55. Very interesting, right? It looked like that. We remember that it is a still ciphertext over here. This is some ciphertext. In order to get 55, you have to decrypt it. But when you decrypt it, we do get 55. So this is very interesting, and it has a fancy name called homomorphic encryption. And let me show you a showcase of how can we utilize this property in the real world scenarios. So remember, we have Alice over here, and then Alice wants to do some computation, but Alice doesn't want to do this computation locally. She wants to use some services, let's say Amazon, to do this computation for her. So what Alice would do is that she would compute C1, which is equal to encryption under her public key of 5. And then C2, she would generate a public key and a private key, basically. But she would encrypt this one for herself, basically, 5 and 11. And then send this one to Amazon and say, hey, Amazon, this is C1. I'm sending you C1, C2, and the public key, which is E and N, right? We send this computation, these things to Amazon. Amazon would carry out the computation. He would compute C3 equals to C1 times C2 mod N, and returns the result C3 to Alice. Alice received the C3. She would decrypt this using her secret key of C3, and what she would find out is actually 55, right? Very interesting. So Alice is interested, right now, actually, I'm doing very tedious example, but let's say Alice wants to compute, multiply very large integers, right? And let's say she's using, she's running on a, very limited power device, an IoT device, that she doesn't have enough memory to do this multiplication. So, but she can do encryption. So she encrypts these two large integers, send them to Amazon. At Amazon, you have access to more powerful, servers and computations. So you can do that in a very short time. So we would utilize the Amazon power to do this computation for us, and it would return the result to Alice. And Alice would decrypt it and get, the result that she was expecting to. Can somebody mention what is the advantage of doing this computation? Why do we do this? Why do we bother to encrypt them and send them to Amazon? Why not we just send 5 and 11 and ask Amazon to just multiply them for us? All right, so let's talk about it. The reason that we are doing this, because we are talking about the class of algorithms that we call them privacy-preserving computation. Privacy-preserving computation. The idea is that we want to utilize the cloud by outsourcing our computation to the cloud, but we do not want the cloud to learn about what computation we are doing, right? So by encrypting this 5 and 11, we send some C1 and C2 to Amazon, and you know that AES is a strong algorithm. It is not easy to break it. So Amazon would multiply C1 and C2 for us, and then return the C3 at any of this computation. Amazon cannot learn that, we are multiplying 5 to 11. To the eye of Amazon, there are some, numbers that I'm multiplying them together. I have no way to understand what are those two numbers, right? And even after Amazon do this computation, he gets the C3, which is the result. And to the eye of Amazon, that is still some random integer, has no value, has no meaning. It only get the meaning, it become meaningful when it comes back to Alice, and Alice can decrypt that result, and then she gets the result of this computation. So a lot of time nowadays, for example, you want to do machine learning. So this is a very hot topic. The input of your machine learning, you want to train a model. When you want to do that, so basically, you have where you get your inputs. Most of the time, those are private records of some user. Let's say you want to build a new model based on some private information of some hospital patients. And it's a lot of computation to build your model, and then you want to use Amazon to do it. According to the contracts that you make with your patients, you cannot just handing all your patient data to Amazon and hoping that Amazon wouldn't use it, and then you utilize Amazon to build your model. No, that is not how it can work, because you're not supposed to share that data. If anything happened, any information leakage happened in Amazon, it's gonna come with a lot of cost. Normally these days they are talking about $8, $8 per record of data. The record of data could be some dummy data, or it could be very sensitive data. So when you hear some major database, or major websites, the user database, for example, leaks. I don't know, 500,000 records get leaked. So you multiply 500,000 to $8. It's gonna be like a lot of money as a penalty. It's a regulatory thing that most of the countries or courts would charge them to pay. So the best way, if we go back to that patient story, is that the best way that you do that is that you design a privacy preserving machine learning algorithm, machine learning building model, that instead of sharing the plain text of user data, the whole raw records, you encrypt them somehow in some encryption algorithm, so that it allows the server to do the computations on the ciphertext, and meaning that once you do the computation on the ciphertext, those computations are meaningful, and then when you decrypt them, you get the result as if you have done that operation on the plain text itself. So this would be a better approach. You didn't leak your information, you didn't share your patient information with anyone. You just encrypt them with some magic, with some specific encryption systems such as RSA, and then you utilize utilize Amazon to do the computation, to carry out the computation, build your model. And even after Amazon built the model is encrypted. Amazon cannot utilize it. The output of that encrypted model is just some random integers to Amazon, and it would never understand what is going on. But when Amazon would send that result to you, then you are able to decrypt that model, and then you can do that computation now locally using only the plain text data. You don't have to encrypt them anymore, just like a normal model that you would build with some machine learning approach. So I think this is also a very interesting direction in cryptography. So these days, a lot of people are talking about this sort of privacy preserving computation. There could be many different event scenarios where the data is distributed, is not in one center, and so on and so forth. So there are many different scenarios where this privacy preserving computation will come into the play to make sure that you don't leak any information. And on the top, Amazon that trained that model for you does not learn anything about that model. It's just like all random integers to the eyes of Amazon. Right. So I hope that now you understand the value of homomorphic property. So this is very interesting idea. The goal is to, so RSA, if you look into the RSA, if you just multiply these values, you get the multiple of the messages. But if you add them together, you never get the add of these two things, right? So meaning that some crypto systems are able to do, let's say, multiplications. Sometimes they are, in some cases, are able to do additions. But those encryption systems that we call them fully homomorphic encryption system, they are able to do addition and multiplication at the same time on the ciphertext. So we would call those algorithms as fully homomorphic encryption. So far, it looks like that designing a fully homomorphic algorithm is extremely challenging. There are some algorithms that work well in theory, but in practice, the cost of encryption and decryption, they are polynomial time algorithms, but the degree of the polynomials are quite high. So it is not really economically, from economical point of view, they're not very efficient so that you could do in practice you do a lot of computation on them. In theory, they are fine. They are able to do arbitrary computation. Remember, as long as you can do multiplication and addition, then you can turn them into subtraction and division as well. So having addition and multiplication would be enough for us to do all other operations as well. But it's just sadly the cost of this algorithm is a little bit high, and it just works mostly in theory. We won't use that in practice. So it is still a quite hot topic for somebody to come up with another algorithm that is fully homomorphic, and then the cost of the operations are quite low. Then we could leverage a lot of new applications and a lot of things that we can solve now in a very efficient way. We would be able to do it very quickly using those algorithms. All right. Any questions?